This week's activity is milling, which is the second of the machining processes that we're going to do. And before we go on to the parts of a mill, I wanted to talk briefly about the goal of today's activity. We're going to machine a product, kind of like how we did in the turning lab. Remember that we turned a piece of hot rolled bar stock into this finished part, and we evaluated the surface finish across some of these sections when we did. We're also going to be evaluating surface finish today on these work pieces right here. But the goal here is to do more than just an evaluation of the surface finish. You can see down here that we cut these pieces of material from stock in one of two directions. And in lecture, you've learned about the rolling direction of material. When we roll steel into bar stock, it generates a grain structure. And we want to see evidence of that at the end of today's lab. So after this clip, I'm going to go into the lab. We're going to go over the parts of a mill. I'll talk about all these. And then I'm going to machine these bars into a notched impact specimen. Actually, each bar will yield a pair of impact specimens. And then we're going to break them. And the break will hopefully indicate to us the rolling direction. So there's going to be some deformation, and of course the impact strength itself will help us to determine that. If you were in lab doing this activity as part of an in-person semester, you would not be told what rolling direction you have, and then you would have to assume that or figure that out based on the results of this test. So after we machine these specimens and test them, I'll walk through some of the logic behind determining whether these bars are perpendicular or parallel. This week's activity, just like last week, is going to begin with an explanation of the parts of the machine that we're working on. The machine in front of us is a vertical milling machine. It's called a vertical mill because the spindle is oriented vertically. The parts of this machine will start at the bottom with the base. The base is connected to the column, and those are typically connected, cast as one piece. On top of the column is the ram, and the ram slides the head back and forth. The head is this assembly right here, which contains the spindle and quill, which move up and down, as well as the drive motor and the drawbar. And we'll talk about the drawbar a little bit when we talk about work holding and tool holding. But the head assembly of the mill is actually what holds the cutting tool here in the spindle. And then we, of course, move the workpiece around on these assemblies here, starting with the knee, which is down here. Knee moves the workpiece up and down, or forward and away from the cutting tool. Some people refer to this machine as a knee mill. So the knee moves up and down. Sitting on top of the knee is the saddle, and the saddle moves back and forth in the y-axis. And then on top of the saddle is the table. The table moves left to right. So between the knee, the saddle, and the table, we can move our workpiece in 3 axes. And then the tool up here in the spindle can also be lowered using the quill, which is just like the quill on the tailstock of the lathe that we used last week. I'll bring the camera over and we'll get a little bit closer picture of the vise, which is sitting up here, and we'll talk a little bit about tool holding. Our discussion on the parts of a mill continues here, now that we're a little bit closer in. On top of the table sits the vise, and the workpiece gets clamped in the vise. We'll get to that in a second. But I mentioned that there was a drawbar at the top of the head of the mill. And what the drawbar does is when we want to hold on to our cutting tool, which is this end mill right here, the end mill sits in a tool called a collet. The collet is slotted, and it has a taper, and there's a mating taper here inside the spindle. So when we load this tool into the spindle, the drawbar is threaded on the end. I have one here. So here's the drawbar with its hex shank at one end, its thread on the other, and here's another collet. As we tighten the drawbar, it will draw the tool and collet assembly up into the spindle. And as it draws this up, then this taper tightens down on the tool. So as we tighten down that drawbar, it will hold this tool in place. Now we have to hold on to the work. Now you can see that the workpiece is too small, and it would easily just fall into the vise where we couldn't get at it. Our goal is to machine all four sides of this workpiece to a very specific size. So what we're going to do is make sure that there's no chips in place, and we have these things called parallel bars. Parallel bars are very precisely hardened and ground pieces of steel, and they sit in the throat of the vise, and they allow us to clamp on our workpiece in a way that keeps the bottom of the workpiece very parallel to the table. These parallel bars will allow us to machine the workpiece itself parallel. Now, one of the things you'll see me do is after I tighten on the workpiece, I will tap it with a lead hammer. And what that does is that will seat the workpiece down on these parallels. You see, as these vise jaws close, because we're gripping on a workpiece that's at the very top, this vise jaw wants to move up. And when it moves up, it lifts off of the parallels. So by tightening down on this, these parallels won't move. Then we know that the bottom of the workpiece is very parallel to the table, and now we can bring our work over, bring our cutting tool down with the quill, and we can begin the process of milling. Today's process is going to yield some notched impact specimens that we're going to cut out of pieces of material that we're not really sure which orientation of the grain they have. In order to do that, I'm going to set each piece in the vise, and we're going to machine parallel sides, opposing sides, with each two different cutting tool materials. So I have tungsten carbide end mill here and a high-speed steel end mill. Just like in last week's exercise, we had high-speed steel lathe tool and a tungsten carbide one. So I'm going to load the high-speed steel end mill in, and I'm going to start by just taking a light cut across the top. I'll make sure that my vise is very clean and that there are no chips that the parallels could sit on, because that would compromise the parallelism of the finished part. So I'll start by clamping up on the workpiece, set it down on the parallels, and then I'll load my cutting tool into my collet. Now each of these cutting tools is a 1/2 inch in diameter. That makes the math for RPM quite simple. We're going to use a cutting speed of 100 surface feet per minute for high-speed steel, and we're going to use 300 surface feet per minute for the carbide. Since this is high-speed steel and the diameter is 1/2 inch, we can apply that in our formula, and we know that 100 times 4 over the diameter of the cutter, which is 1/2 inch, will be 800 RPM. So I'll turn on the machine, and I will set it to 800 RPM, and I'll make our first cut.
I know that was a little bit blurry, but what you should see here is that our surface finish is much better. We've raised a burr here on the edge. We're going to have to grind that off because the next step is going to be to flip this over now and machine this surface. But we have a much better, flatter surface here on the machined face than we did on the saw cut face. I've now deburred the edges of my workpiece, which is important because now we want to grip on this surface here, and a burr would interfere with our ability to grip on that. I'm going to load it back in the machine, and I'm going to take a light cut off the top and then measure it. Now before I can do that, I need to sweep out the throat of the vise to make sure that there aren't any chips in there. You'll notice that I'm going to hang the workpiece off the edge of the vise just slightly. And what that's going to do is allow me to access it to measure the thickness. So now the spindle speed is still set correctly. So now we'll take another light cut. Now you'll see the reason why I overhung the part a little bit was so that I could get in with my micrometer and measure this. So I measure that as 0.459, which means that we need to take 59 thousandths off. Now just like last week, there was a depth of cut to be considered, and if you were in the lab, you would see that I would request that no more than 40 thousandths depth of cut be taken off at a time. And I'm going to do the same here because the depth of cut plays a similar role in milling as it does in turning. So I'm going to make one cut that's 19 thousandths and one cut that's 40 thousandths. I've now made my two cuts of 19 thousandths and 40 thousandths, and now I'm going to measure my workpiece again. I have a tolerance of plus or minus 5 thousandths. That looks like 0.4 inches, pretty much on the money. Now I can remove the workpiece, and now I'm going to repeat the process with a carbide end mill. So I'm going to turn the workpiece 90 degrees, machine one edge with carbide, flip it over, machine another edge and check the thickness, and then I'll cut this down until this one is also 0.4 inches. Okay, now I'm ready to make my first cut with carbide, but because I've changed the tool material, I need to calculate a new surface speed. We use 100 surface feet per minute for the high-speed steel tool. So 100 surface feet times 4 divided by the 1/2 inch end mill gave us 800 RPM. For carbide, we want to use something closer to 300 surface feet per minute. So that's going to get a little bit faster, quite a bit faster. So 300 times 4 is 1200 divided by 1/2 is 2400 RPM. So I'm going to set my mill to 2400 RPM and then take a first cut. So there's our finish from the carbide. Again, we have a burr that's formed, and so I'm going to take this back over to the sander, knock this burr off, flip it over, and then I'll repeat the process for the carbide sides. Okay, so now I have completed machining all 4 sides, so all of the mill scale finish is gone. And now the next step will be to cut this in half and then put our notches in, and we'll get a pair of 2-inch specimens out of this. Now I'm going to machine our second one off camera, because these two should give us a comparison of materials that are cut parallel to the grain and perpendicular to the grain. Of course, we don't know which is which, but after we impact test them, we will. Now the work pieces that we want to notch are actually only 2 inches long, and we've started with 4-inch bar stock. So I've scored each one of these at 2 inches, and we're going to use a band saw to cut them. So in here is a continuous band, toothed, made out of the very similar material to the high-speed steel tools that we've been using. And when I turn it on, the band will advance continuously, and we'll use it to cut these specimens. Now this also leaves a bit of a burr, and so I'll take that to the sander and sand that off, and then we'll take each one of these 2-inch long specimens and notch them. Okay, I now have our workpiece clamped here in the vise of a horizontal mill. The horizontal mill is named so because this spindle is horizontal in direction, and this angled cutter is what I'm going to use to make our cut. And here's another view of the notch being cut. I wanted to give you another view so you saw what the profile of the cutter looked like. Now it is time for us to test our specimens. So I have our 4 specimens cut from the 2 4-inch bars, and we're going to test them on this machine. This is an impact testing hammer. It's got this big pendulum, and when we bring the pendulum up and we set this scale, we can drop the pendulum, it swings through and breaks the specimen, and then it will absorb how much energy was absorbed. It will show how much energy was absorbed by the specimen. So we're going to set this to 0. We're going to load our first specimen in place. So the first specimen absorbs 75 foot-pounds of energy. Now that 75 foot-pounds deformed the specimen as it broke. You can actually see, if the camera will focus. Oh, it might not focus. You can see that there's evidence of deformation before it broke. So that's what gives this impact strength, is the ability to deform, kind of like the crumple zone in a car deforms and collapses. So you can see where it necked here before the specimen broke. Now that specimen absorbed 25 foot-pounds. The 25 foot-pound specimen, we can see there's much less evidence that this specimen deformed. It looks like it was actually almost like a clean break. So significantly different and significantly less impact strength. That specimen took 80 pounds to break. And here we can see again, still one piece, still totally didn't break. I could probably break it with my fingers if I tried. But here there's clear necking as this deforms as it breaks. That deformation indicates impact strength. And 80 foot-pounds is what it absorbed. That specimen absorbed 20 foot-pounds. And here again, clear, clean breaks from the 25 and 20 foot-pound specimens.
Now that we've broken our specimens, we can discuss a little bit the goal of the exercise, which was to identify the rolling direction for the material from which these bars were cut. Now, in order to do that, we can first group these bars into two groups. There's the relatively low impact strength specimens on the left and the high impact strength on the right. And we call those low and high impact strength not just because of the numbers, but there's the physical deformation that occurred over here that slowed down that ram. Again, like the crumple zone in a car. So what are the implications of that in terms of the material from which this was made? Well, if we think about the workpiece, which was a piece of bar stock, and we think about this being rolled out of the mill, if it's rolled in this direction, there's going to be grains that form, sort of like the grains in a piece of wood. Now from this piece of stock, we cut specimens. Some specimens were perpendicular to the grain, and some were parallel to the grain. So which one would have the higher impact strength? Well, if you think about it, this specimen right here, the perpendicular to the grain, would have grains running straight across, which is exactly where we tested it. The grains would split, kind of like when you take a maul or an axe to a piece of firewood. It would just split with relatively little resistance. There wouldn't be any deformation. Now consider over here, we have grains that run along the piece of, we'll call it wood. Now when we strike it, imagine trying to break a 2x4 over your knee. It would take a huge amount of force, and even when you did break that 2x4, there would be huge amounts of deformation. So from that, we can conclude that the specimens on the left, which were relatively low in impact strength, came from a cut in the material that was perpendicular to the grain. That is, this cut was made perpendicular to the grain. And then the high impact strength ones were cut parallel to the grain. So hopefully that gives you some in-action knowledge of how that grain structure affects the workpiece. Even though these materials look like they're totally homogeneous at first look, they are not, and that grain structure does play a major role in the strength of the material. But other than that, hopefully you gathered some information from the process of milling, including some applications of feeds and speeds, as well as chip making, just like you saw last week, but now with a little bit different orientation on the vertical mill.